welcome everyone. Welcome to this TILOS HDSI seminar. It's really a great pleasure to welcome and introduce today's seminar speaker, Petar Veličković. So Petar is currently a senior staff research scientist at Google DeepMind, and I believe he's also affiliated lecturer at the University of Cambridge. That's his alma mater, where he completed his PhD from. So Petar has done many very interesting, impactful research across a broad range of topics, including graph learning, geometric deep learning, and also more recently in neural algorithm reasoning. Okay, so just to give you a few highlights, many of you probably use the graph attention networks, and Petar is the first author co-developed this GAT. Okay, very widely used. He also co-authored the book Geometric Deep Learning together with I think Michael Bronstein, Joan Brunner, and Taco Cohen. Okay. He is also a pioneer on this topic of neural algorithmic reasoning and developed the CLRS algorithmic reasoning benchmark. I think today's talk will also be along this theme of developing machine learning systems that are aligned with algorithmic computations, which I think is a really interesting, exciting topic. Okay, so I should mention that his work has also been featured in various media outlets as well. So we're excited to have him. Now, without further ado, Petar, welcome, and the floor is yours now.
All right. Thank you so much for kindly inviting me to speak to your seminar, and thank you for coming to my talk, everyone. As mentioned, my name is Petar Veličković. I'm a senior staff researcher here at Google DeepMind in London. And I also hold an affiliate lectureship at the University of Cambridge. And today I'll be talking to you about some of our recent work in trying to use artificial intelligence to amplify human performance in combinatorial competitive programming. And I would say that the result I'll be talking about today is certainly a very fun result. It'll be obvious why I'm bold-facing the word fun later on during this talk. And this is, some of you have probably seen the paper, which has the same title as the talk I will be giving today. It is certainly an area that I'm very passionate about, and it is a result that made us quite excited when we first accomplished it. And indeed, eventually, we will make our way towards this result. But I do think that diving right into what happened with this result without contextualizing it a bit is probably not the best way forward. So actually, before I dive into the fun stuff, I'm going to give you a little bit of background. And in the process of that background, I'm going to present to you a few works that I was involved in before, which generally try to set the stage for, I guess, my personal flavor of how I like to approach AI research and which projects in AI research I personally find most motivating. Specifically, I am very excited, generally speaking, about artificial intelligence research that can amplify human capabilities. And perhaps the first example of this that I had the chance to be involved in was our work on artificial intelligence for helping pure mathematicians. And you might be interested in, like, how could artificial intelligence benefit pure mathematicians in their research? Maybe today with the rise of chatbots, that's not so hard to imagine, but this was research that we've done in 2021 where chatbots were nowhere near as risen as they are today. And it was actually quite challenging to even find mathematicians that were willing to consider the idea that AI might potentially assist them in their work. So how did we decide to create an ability amplifying method in the context of research mathematics? Well, we realized that very often when mathematicians have to reason about various mathematical constructs, they have to analyze really complicated objects. And okay, maybe they understand these objects enough to write a program to generate them. But then what this program gives them is usually nowhere near as easy to analyze. Often it will have this really complicated graph structure with lots of different objects and edges between them. And it's not easy to then go from an object like this and kind of prove a regularity or prove that there is a condition that must be true, especially not when you plot it like this, right? But you could take that object, feed it into an artificial intelligence system like a graph neural network, and then that system will, rather than solve the problem for you, which is arguably still out of reach of the systems as they are today, it can instead suggest, maybe in this sea of nodes and edges, what are the most meaningful nodes and edges that you should be looking at. So, so that rather than looking at thousands of nodes, you can only look at 20 or something like this, and their local subgraph. Now, I must stress, our system is not perfect. It's not going to give you exactly the nodes and edges that you need to look at to prove your theorems, but it does contain sufficiently salient information that when you were to show these examples to a mathematician, they might find something to go on, right? And certainly it's much easier to analyze even a noisy graph of 15 nodes than a less noisy graph of 1,000 nodes, right? So a mathematician might look at some of these suggestions of like, here are the subgraphs you should focus on. In this case, these are these diamonds at the bottom of the graph. And, this might inspire the mathematician to come up with a new idea. Maybe they'll be able to conjecture new approaches for unsolved problems, or they might even be able to prove stuff towards a problem where humans historically haven't been able to make a lot of progress by themselves, just because the objects are really complicated to reason about, even though we might be able to generate them. And we have been able to take this idea and deploy it in two very disparate branches of mathematics, specifically knot theory and representation theory. We worked directly with the research mathematicians who took the insights coming out of these graph neural networks and then used them to prove the necessary statements by themselves, right? So really, the AI wasn't, in this case, this was in 2021, it wasn't doing the proving for the mathematician. It was really telling them where to look. And then that was really all it took. Like, this initial motivation turned out to be quite important. And the fact that we were able to basically use the same blueprint in two very different parts of mathematics and derive research that was publishable in a top-tier math journal caught the attention of the journal Nature, which featured our work on the front cover. This was in December of 2021. It also led to a reasonable amount of attention in the popular media. But really, what I personally cared about the most in this research was the reactions that we would receive from the mathematics community, which really are going to be the main users of research like this. And indeed, the reviewers of our paper for Nature itself had claims like, this paper marks the beginning of a new phase in use of computers in math research, or I cannot imagine a mathematician not using a method like this if available to them. So we've basically there was this 180-degree turn where initially it was very hard to convince anyone in research mathematics that AI could be a tool worth considering. And, papers like this one were one of the first strong pieces of evidence that maybe mathematicians should consider the use of AI as a helper tool. And as I said, the individual contributions we've made to knot theory and representation theory were then published in top-tier math journals. In this specific case, the representation theoretic result, where we used the graph neural network to analyze what were the most important subgraphs of a so-called Bruja interval, led to new results towards the combinatorial invariance conjecture, which is one of the very important questions in representation theory that hasn't really had progress on it in the past decades. And using these insights, Jordi Williamson, who was the mathematician working with us on this, was able to make very meaningful progress in this space. And not only were we able to publish this in a top-tier American Math Society journal on representation theory, but also it led to a plethora of follow-up work, which basically used the structures we've discovered with the help of AI and then built additional theory on top of that. And actually, for example, this follow-up work from Barclay and Gaetz was able to take the basic framework that we've established and then make additional proofs that our conjecture holds for specific subintervals. And one of the fun kind of side effects of that is that because of the way constructs are named in mathematics by the authors of the corresponding paper, I now have a polynomial and the conjecture partially named after me, which I thought was a pretty cool side effect of doing this research. Okay, so the first part, as I mentioned, is the use of AI to assist mathematics research. That was a pretty good start, and showed to me that really a research like this can have huge potential. Then the second thing I want to show you is maybe something you would not expect in this talk. It's something certainly that we would consider a little bit more fun, but no less challenging. It is the use of AI for sports. Okay, so we have recently, well, it was actually a multi-year collaboration, but especially in a few recent years, we have worked on how can artificial intelligence methods be used to improve sports analytics, and specifically because we are a company that was at the time firmly based in the UK. We worked on football analytics, which in the US you would call soccer, together with one of the best football clubs in England, Liverpool Football Club. And together with their research team, we have developed a method that you might now know as tactic AI, which was also quite reasonably successful in the research community. So let's discuss a little bit, what do we mean by artificial intelligence for football, and why might something like this be even an interesting thing to think about, and how this might lead to ability amplification or acceleration using AI. This was a picture that we've taken when we visited Liverpool for one of our hackathons. That was a pretty fun time. And specifically, the methodology that we have created, Tactic AI, was, to the best of our knowledge, one of the first systems that went beyond being a simple research prototype, in the sense that it was, just a machine learning paper that tries to train on some football related data and then try to answer some questions better than a baseline. This was our real first attempt that we were aware of to actually build a system that was capable of meaningfully answering things that could practically become useful on the pitch. And the significance of this collaboration and the outcome of it was actually recognized by Nature Communications, where we published this work last year. And as far as I know, it's one of the very few, or maybe the only, sports analytics paper to reach a journal of this level. So clearly the community has taken some notice. And one thing which is important to note as to what Tactic AI is capable of is, we started off with something that you could classify as kind of traditional machine learning and predictive modeling. So say, taking a particular football situation, what will happen? Who will receive the ball? Will there be a shot on goal? Things like that. So these are the kinds of things that might help accelerate the work of data scientists, because they're going to be able to analyze more situations and reason about maybe possible counterfactuals. But then, once you train a model, we didn't stop there, right? When you train a model to predict outcomes in such a complex game involving, human agents and kind of potentially even longer horizons, that model had to have built a decent understanding of the game, right, in its internal representations. And that's something that you can then exploit to potentially find similar situations that you might not otherwise easily notice, that have similar kind of strategic patterns compared to a reference situation. So indeed, we took the embeddings from the predictive model and we used them to build a retrieval system. It's as simple as, you take your corner kick situation or a similar set piece situation, you use the pre-trained model to embed it in some high dimensional space, and then you retrieve similar situations by just mining in a database using these embeddings. And this is actually one area where the system we developed can make a very meaningful effect on accelerating the work of people in the club. So top tier football clubs nowadays employ video analysts whose job is basically to watch many pieces of video content on previous strategies performed by a particular team, by a particular opposition, maybe even by particular players, to kind of make sense of all that data and to prepare meaningful reports that then coaching assistants can use to actually drive insights and prepare the players for what awaits them in their future matches, right? So if those video analysts had any tool that could be like a YouTube recommendation system, right, to tell them, based on this video you just watched, I recommend you should watch these 10 videos next, that could accelerate their workload by a lot and kind of make them more focused on summarizing the insights rather than making sense of what is the next video I should watch based on everything I've seen. So the retrieval module actually has a very direct impact on potentially accelerating the work of video analysts. And lastly, but not least, you could also use systems like these for generative modeling. So you can not just reason about a situation that has happened in the Premier League, but also reason about changes. Like, what could we do? How could we modify a particular tactical situation such that, for example, the probability of scoring a goal is increased or decreased? How should I move my players or reorient them to make a particular outcome more or less likely? And this is something that's more directly targeted at coaching assistants, right? So you can feed a particular situation, a particular tactical setup, and Tactic AI can immediately recommend changes of position for different players. And I should stress, this model was trained as a conditional variational autoencoder. So it hasn't been trained to suggest tactics. It was trained to reconstruct, right? We've done this on purpose because we did not want, you can easily amplify the probability that a shot will happen if you just move all of the defenders in some stupid position, right? So we wanted the predictions to still be realistic. And as a result, we trained the model to reconstruct, but conditioned on whether or not a shot happened, for example. So that in test time, we could take an actual situation and flip that flag and see what the model will generate in a kind of the counterfactual scenario. And because these are small changes, this is not something that kind of meaningfully translates into brand new tactics. However, it allows the coaching assistant to immediately see, oh, these players are most modified by the model. Therefore, the tactic might be critically dependent on what this player does or something like this. If this is one of our players, then maybe we need to coach them better to exploit such situations. If this is an opposing player, then maybe we can exploit any weaknesses that the model has discovered in this way. And once again, this doesn't really replace the role of the coach. It only accelerates the pattern matching stage of what they have to do, because there's 22 players on the pitch. There's lots of different things happening. Making sense of that and meaningfully kind of doing next steps as a result is tricky, right? So altogether, Tactic AI, you can think of it as a full AI system giving useful tactical suggestions to coaches. And this was really the motivation. Like, we did not just want to build a machine learning system capable of doing this or that in the football context. We wanted to make it useful. And this was also recognized a fair bit in the popular media, from the Financial Times to New Scientist to El País in Spain. And these two, I just wanted to start with these two to set the stage of this general idea that I am motivated by building AI systems that will accelerate and amplify the work of humans, right? And this brings us to competitive programming, which is the third area, which obviously most of this talk will be dedicated to. But I hope that the first two kind of give a nice flavor of like, how did we get here, and why do I have such an eclectic output of different things which can't very easily be related? There is actually a very nice thread unifying all of those. So my dream, actually, I've done a lot of competitive programming and theoretical computer science and algorithms when I was in high school, when I was doing my undergraduate degree. When I started to get into AI, I had a dream of building an agent that was capable of beating me in competitive programming. And, I'm not the best competitive programmer there is, but I've had a decent run. This is actually a picture of my team, which was able to win first place at an ACM ICPC regional competition. So this is not on the level of the best competitors in the world, but among the level of some of the best university teams in Northwestern Europe, which is where the UK belongs. However, that dream was effectively steamrolled in December 2023 with the release of AlphaCode 2. So AlphaCode 2, which was a competitive programming agent from DeepMind, was able to basically reach the 87th percentile of all human competitors on Codeforces, which is a popular programming competition platform. And this was roughly the same level that I was at. So at that point, this really ceased to be an objective for me. But kind of following on from the directions of what we've discussed in the previous steps, I was then interested to see, can we build an agent that meaningfully improves what human competitive programmers can do by themselves? And this now allows us to segue into the FunSearch method, which was the key behind what we have built in our approach. So one of the main kind of missions of the FunSearch team, which I'm not a member of, but they have allowed me generously to use some of their slides to present the key ideas of the method. One of their main objectives is to discover new knowledge and efficient algorithms for impactful problems with the use of artificial intelligence. And as we will see in a few slides' time, through the use of FunSearch, it is actually possible to do this. So the setting where FunSearch is particularly applicable is when you have access to a language model and you have access to an evaluator. And this is actually a fairly common setting. Many problems you care about will allow for a fast evaluation function. So if you give a particular candidate solution, you can evaluate how good it is, right? But actually solving the problem is not so easy in many cases. So what FunSearch does is it has a language model that can generate a possible solution, but it also uses the evaluator to guard against solutions that are incorrect. And in the process, it allows itself to iteratively improve the solutions using the guardrails of the evaluator. This is an important thing because most modern language models, when you ask them to just flat out solve the problem, if you try to get them to iteratively improve, eventually more and more issues will creep in. But if you have the guardrails of the evaluator, then you can just easily discard things that don't fit the specification you're after. And to illustrate this, I will talk about one of the specific problems that the original FunSearch paper investigated, and that is the capset problem. It is the problem of finding the largest set of points on a d-dimensional grid of 3 items in each dimension, such that no 3 of them are collinear. I'll illustrate the problem in a few moments in various dimensions. But one thing that's interesting to note about this problem is that Terry Tao, one of the most well-known mathematics researchers today, has quoted the capset problem as perhaps his favorite open question. So basically, let's analyze what this problem is about by studying it in some specific dimensions. D equals 1 is maybe the easiest one. You have exactly 3 points on a line, and you have to pick what's the biggest number of points you can take without any 3 of them being collinear. Well, the answer to this is clearly 2, right? You can take 2 of them, but you cannot take the third one. At that point, you have completed a line. So the largest cap set in D equals 1 has size 2. What happens in 2 dimensions, right? Now you have a grid which is 3 by 3, right? And in this case, you can hopefully convince yourselves that, okay, I can take a point in the corner, I can take the points immediately adjacent to that, and I can also take the point completing the square, but I actually cannot take any additional points. And actually, you can convince yourselves that in 2 dimensions, the largest cap set has size 4. Right? You cannot add a 5th point. There is no configuration where this is possible. Now, if you look at 3 dimensions, already this becomes a little bit more complicated to draw, but it is possible to show that actually in 3 dimensions, the best cap set has size 9. And this is already a step up from what you've seen previously, right? Because if you were to follow the simple local square solution, you would get the number 8. But actually, if you're careful enough and you wiggle around in the 3 dimensions properly, you can find a cap set containing 9 points. And actually, we know how to solve this problem up to 5 dimensions, up to 6. 7 dimensions and above, this is an open problem. We actually do not know what is the biggest number of points that we can have in the cap set. And naturally, exhaustive solutions become complicated at this point, right? Because the brute force just doesn't work. So obviously, we do have some constructions, but can we discover better ones than what was previously most known to mathematics? So let's just think about the capset problem from the perspective of what I've told you before, what makes FunSearch good to apply. First of all, you can verify the correctness. So if I give you a candidate set, you can, in polynomial time, check whether this is a capset, whether there is any 3 of them that are collinear. And you can also measure how good it is. So there is a clear evaluator function and a scoring function, right? And this scoring function just says, okay, assuming that it's correct, how many points do I have in my set? So it's a very simple score function. So using these two parts, we can write an evaluate function which terminates in polynomial time, and we can use it as our guardrail, right? Now, if you have an evaluate function, how can you then use it to improve your solutions? Well, you guessed it, we can use a language model that writes some code to solve the problem, and we can then ask that language model to evolve the code to get better at solving the problem in the code space. So you write something like this. This is actually a very simple first version of the code that you can write. And okay, so you have a function that will build your cap set in a particular number of dimensions. You have your evaluator function, which will check whether a particular collection of points is a cap set. And let's say you start with a very simple heuristic for a cap set, checking whether you will pick a point if its first dimension is 0 and its second dimension is 0 or 1. So this is a very stupid heuristic, but it's something you can write as a first possible solution, right? So the idea is you can then ask FunSearch to use your build function to build a candidate and then run evaluate to check and score whether this cap set is correct and how many points it contains. And what you do then, right, is you create a prompt like this. So you call your previous stupid heuristic the V0, and then you ask your language model to write a V1, right? So you ask it, given my evaluator, given my previous best solution, write me a better solution, right? This is the question. And you might then expect that your language model will realize that this check is too stringent, and it might instead realize that you could constrain both the first and the second dimension to be less than or equal to 1. And this actually discovers the optimal solution in 2 dimensions, right, as we discussed before. So the previous stupid solution will give you a cap set of size 2 in 2D, but the improved one will give you a cap set of size 4, and that's obviously better. And what you can do then is just rinse and repeat, right? You can substitute your V1 to be the V0 and then ask the language model again, produce the next one, right? And you keep doing this over and over again. And since you have the guardrails of the evaluator, you can discard the solutions that are incorrect and just not think about them. Now, in practice, just doing one chain of iterative improvement isn't necessarily going to give you the right outcomes. It might easily get stuck in local minima and things like that. So generally, it's good practice to wrap all of this in a procedure that can fight against those issues. And one such candidate is a genetic algorithm, or more generally speaking, an evolutionary procedure, right? So you start with your V0 and you have your target optimum here as a star. You initially basically use the language model as a mutation function, right? So it predicts many possible candidate programs based on where you are right now. And your model can then kind of follow the most promising chains, discarding the less promising ones or ones that fail to compile or match your API or whatever. And, gradually in the process, get better and better at your scoring function, right? So let's see how well this works when applied to the cap set problem. In the top row, you have the previous best cap set sizes known to mathematics at the time when the FunSearch paper was written. And at the bottom, you have the best constructions found by FunSearch. One thing that's pretty cool is that actually FunSearch reconstructs all the previous best known results, 2-dimensional, 3-dimensional, 4-dimensional, and so on. But then we get to 8 dimensions, and suddenly FunSearch has discovered a cap set which is bigger than the best previously known cap set to mathematics. Actually, the previous best known one was 496, and it improved it to 512. One other cool part with writing the solution in code is that you can kind of analyze the generic strategy of that code and extrapolate what is the kind of asymptotics of how big the cap set is as you scale that code up to bigger and bigger dimensions. And actually, this found a solution which provably has better asymptotics with n than the previous best known solution of that kind, right? And one reason why it's much easier to analyze a model that produces this is because, a cap set is raw, when you look at it in a raw way, just a collection of points, right? And it's really tricky to look at that raw list of points and make sense of that. But instead, FunSearch doesn't give you a raw list of points. It gives you code, just, some Python that you can look at. And arguably, it's much easier to make sense of the thing on the right than it is to make sense of the thing on the left, And actually, this was the first discovery made by the FunSearch team. And it's quite a significant one. To the best of our knowledge, this is the first scientific discovery made using a large language model, in the sense that it's a provably new piece of verifiably true knowledge about a relevant problem in research mathematics, right? And also, it's a new computational paradigm. It's an idea to use computation to discover understanding rather than just regurgitating facts. And beyond the fact that we were just able to move the needle, we also got some pretty cool comments from mathematicians who worked with us, like Jordan Ellenberg, who basically said the solutions generated by FunSearch are far conceptually richer than just a list of numbers. When I study them, I learned something. So it's not just that you have better combinatorial optimization. It's also that whatever comes out of the system is meaningful.
And I have a quick question. So
yes.
This is really interesting. So did the code discovered, was that the code itself already extend to higher dimensions? I mean, or it's still hard coded for a fixed dimension, then you all read the code and then kind of extrapolate that.
So the way in which, and I noted this down, basically the way in which the code was extended is by basically finding this finite construction or admissible set that would imply a particular asymptotic bound. So there were a few steps that were additionally necessary to prove this. But obviously the code is a great first step, and then a mathematician can make sense of it and go ahead and prove stuff, right? So yeah,
Thanks.
kind of in line with the first AI for maths results that I showed you at the beginning. Okay. So now we can finally talk a little bit about competitive programming, which was the promised topic. Thank you for bearing with me for half an hour, but I do hope that you've learned something interesting. So with the release of FunSearch, as I said, I'm not myself part of the FunSearch team, but I was really excited by this release because it was a very different, at the time, it was a very different use of large language models to basically anything else that was out there. And I thought, okay, this can be a pretty good fit in a type of competitive programming, which, as I said, is my personal objective. And specifically, we looked at combinatorial contests. One example of combinatorial contests is hash code. And hash code, for those of you who are unaware, was a combinatorial competitive programming challenge organized by Google over many years. And it was basically a collection of NP hard challenges, kind of like the CAPSET problem, where you have to produce the best possible solution on some given test cases on engineering problems that are of relevance to a company like Google. And you can see, for example, this one problem that was in the qualification round in 2020 is the task of finding optimal ways to scan books to Google Books so that you can get the most coverage of the literature, knowing that certain libraries have different volumes and they might also have different capabilities of scanning different numbers of volumes per day, right? So it's basically a standard scheduling problem, which a typical software engineer in a big tech company has to encounter on a regular basis, right? So specifically, the way we have decided to leverage FunSearch in this case is we first for FunSearch to be efficient, you need to build a good environment for it to hill climb in. So our idea was, okay, we as the competitor can implement a simple backbone of something like a greedy algorithm. So something that will, select items one at a time based on some heuristic. And then FunSearch can evolve the critical part of it, which is the scoring function, right? So deciding what is the next item you're going to put into your partially constructed solution. And then based on what comes out of FunSearch, you might learn some new things about your problem. So you might change your strategy, put on some extra local search or something like this. The idea with this is that we really want to mimic what a real competitor would do when they approach a contest like this, right? So typically, you would write an evaluator function, you would write a basic greedy algorithm, and then you would spend some time trying to evolve that algorithm, try to make it more smart or use some insights about the distribution of the test data that you can observe, right? And really, it's that synergy between, the human competitor who orchestrates this basic kind of setup for the AI to operate in, and then FunSearch can kind of use that environment when it's built properly, right? And it's important because, recall, problems in competitions like hash code and CAPSET problems are NP hard problems, right? These tasks, as we know, they're inherently hard for humans to solve without some degree of brute forcing. So you need to resort to these kinds of intuitive heuristics, right? You need to kind of have this leap of faith to see, oh, there is something about this problem which is important. I'm going to try to use it to build a more accurate heuristic, right? And then, while AI might be a tool that will help us do many things a lot better, AI is fundamentally a polynomial time algorithm, at least most of the systems that we know of so far. So it does not improve on the P versus NP debate, right? So what was intractable before AI will likely stay intractable after we develop AI, in the sense of complexity theory, at least. And when you think about some of AI's greatest successes, it was usually in environments where there's a robust environment, and then they can meaningfully hill climb and correct their mistakes in it. So think of things with a good simulator like AlphaGo, AlphaStar, and those kinds of things, right? So the idea here is that humans working together with AI can do what neither can in isolation, right? Because the human prepares an environment which will allow AI to thrive, right? By writing the evaluation function, the greedy algorithm, and so on, you basically have this good, rigid construction where AI can continue to evolve. And then AI does what AI is good at, right? We train over the entire internet. We absorb the data on how humans write their heuristic across a wide range of problems. And then you can kind of evolve your own heuristic by interpolating over whatever are the best, most clever human strategies you can find in your training data, right? And those evolved heuristics then inform better guided environments. So it's a process that can really go hand in hand. So we tried this approach, and we ran it on every single hashcode qualification round from 2015, when it was first created, to 2022, which was the last year when hashcode was held. We deliberately chose the qualification rounds because the qualification and the final rounds have equal, they're both NP hard, but the qualification rounds has a lot more teams. So we have a much bigger cohort to compare against. And these are the results we've been able to achieve. As you can see, these are pretty solid ranks. In half of the competitions, we've been able to receive a score that would match or exceed the best human team at the time of the contest. And in the other ones, we were also quite successful, reaching basically first percentile level performance. Now you might wonder, okay, but could we have achieved these kinds of results by ourselves? As a point of comparison, I have personally competed in the hashcode qualifiers for several years, and you can see my scores on the right-hand side. Clearly, this system was able to achieve a higher rank than what I was able to do when I was doing these contests. And actually, 2021 is a really interesting year, because in 2021, I was part of the hashcode organizing team. So what we do at Google is, we internally battle test these rounds before we give them to real competitors by just, asking Googlers for 2 weeks, try to come up with the best possible solution that you can for this problem. And the best Googler at that time was able to achieve a rank that would be equivalent to rank 20, right? So in a sense, it was outperforming the human competitors. It was also outperforming what we were able to do internally in a specific amount of time. And I would say this is a pretty clear sign of ability amplification. It is true that these contests have happened in the past, but remember, we're asking FunSearch to evolve something conforming to our own API. So in a sense, it is different from any particular solution that you might find on the internet in terms of evolution, at least. So to illustrate what we've done here, let me show you one specific year, which is 2018. You can find many other examples in our paper, but 2018 was a year that had a particularly easy one to describe. So I'm using this one very specifically. And it was also one of the first rank 1 results we've been able to achieve. So specifically, as the title implies, it's a task to find optimal schedules of self-driving car fleets. Specifically, you have basically a lot of these different cars spread around imaginary Manhattan. So it's basically like a grid of different intersections. And you have a bunch of users of your self-driving ride app all saying, I want to travel from this intersection to that intersection. They all want the cars at different times, and they also prefer to reach their destination by a certain time. Otherwise, you don't receive a bonus. So it's then up to you to decide, based on your fleet of cars, at what point does which car travel to which user, right? So it's a very complicated vehicle routing scheduling problem, right? And the time it takes to travel between 2 points is your usual Manhattan distance. So what we wrote is this particular backbone, where we just maintain a simple structure storing all of the important details about the different rides being requested by users. And we have a convenience function to compute the Manhattan distance. We added some subroutines for parsing the dataset files. And we wrote a simple backbone, which basically, you can see here, there's a while loop where every step of the way we call the function pick ride, which for the current earliest available car chooses which ride it's going to go to. And that's the function that we try to evolve, right? And then every step, while we can still do that, the car that's most recently available picks the ride that our pick ride function gives, and then we simulate what happens as a result of that particular ride being scheduled. And you keep going until you run out of simulation time, right? This also gives you the score of your final result. So we started off, now you might be wondering, what does pick ride do? We started with a really simple function, which actually doesn't do anything smart. It just finds the first ride in the list of rides, which this car can pick up before it expires. And the first such ride, you just return that index. And if you fail to find any such ride, you return -1, which means there's no more rides that this car can pick up at this point in time, right? So we took this as a starting point. We let it evolve. And you can see this initial backbone was not good at all with this stupid solution. It was maybe achieving 30% normalized score, which also would place it in, the worst 20% of the competitors. But you let FunSearch work with it for just 2 hours, and already it's very close to the top teams. You give it a little bit more evolution time, and actually it is outperforming the top solutions. So here on the x-axis, you have the percentile of the competitors, and on the y-axis, you have the normalized score with respect to the top human team. And the green shaded region at the right are the teams that were invited to the finals of that particular year, right? So yeah, you just create this basic backbone, you let the model hill climb, and it's able to just by itself reach these very strong heights. And this same recipe worked really well in all 8 of the years. I've shown you one specific year for kind of a specific example for the self-driving rides, but you can see this is a result we've been able to replicate in every single year that hashcode had taken place. And this was recognized with good comments from people in the competitive programming community. Petya Mitrichev, who is one of the best competitive programmers of all time, and also software engineer at Google, has said that it's an exciting approach to combine human competitive programmers with LLMs to achieve results that neither would achieve on their own. And Przemek Pietrkiewicz, who is one of the lead organizers of the hashcode contest itself, actually wrote a blog post in response to our results saying that this could be seen as the deep blue moment for combinatorial competitive programming. And I haven't yet shown you what FunSearch produced, and now I want to show you a really cool example of that. So I'm going to look at a different year, 2015, where the task was to optimize the positioning of servers on a server rack to optimize a data center. And you can see we started with a very simple backbone solution, which achieves maybe 348 points. You let FunSearch work with this for 2 hours. This is what it comes up with. Like you can see, it loves to add additional logic. It loves to, hallucinate very interesting constants, kind of like what a human competitor would do, tweaking constants to find the best hyperparameters effectively. And within 2 hours, it's actually ranked 2. So the second best team was beaten by this particular heuristic. You let it evolve for a bit longer than 2 hours, it is actually able to steamroll past what the best human team was able to do in this contest and achieves a score of 413. And you can see there's lots of very interesting constants and logic appearing all over the place in terms of what the model was able to do. Now, while I did describe how all of these results on hashcode, you could think of them as possibly half-corrupted results because hashcode contests did take part in the past. We did also want to demonstrate that even if you test it on a new contest that the model hasn't seen during training for sure, it still was able to achieve remarkably. And for that perspective, we looked at one of the very few contests that took place after the language model we used was released. So the language model we used at the time was Gemini 1.5 Flash. And the AdCoder heuristic contest 39 was one of the very few contests that happened after Gemini 1.5 Flash was released. So specifically, this is a very interesting geometric problem where you have a bunch of points of type 1 and type 2, blue and red, in the grid. And your task is to find the best polygon with edges parallel to the x or y axis, such that as many as possible of the red points are inside the polygon and as little as possible of the blue points are inside the polygon. So you need to find basically constructions like what you see on the right that try to hunt for these interesting clusters of red points and just latch onto them, right? So one very standard strategy you can do in this case, because the grid is very fine for you to just manually build this polygon cell by cell, is a standard strategy is to cut up the grid into pieces of a certain size and then just start with a particular cell and have a greedy algorithm keep attaching adjacent cells to that polygon, right? And here you can see how well FunSearch learned to evolve the strategy for different sizes of that coarsening of the grid. So basically, the more coarse the grid, so the bigger the cell, the worse the solution you get can be, because obviously it will miss some important detail, but it will maybe reach those better solutions faster because there's fewer spaces to explore in. And what you can see to our delight is that no matter what specific size we picked, the model was able to hill climb very quickly and actually achieve much better scores than what you'd get with a very simple heuristic, which our simple heuristic was a cell is as valuable as the difference of points of type 1 minus points of type 2, right? So it's a very simple scoring function that achieved the scores at the bottom. And here you can see on the x-axis also how many programs were generated to achieve a particular level of performance. One thing that's really cool about the AHC compared to hashcode. So in hashcode, you had very specific test cases you needed to optimize. So you had a lot of these, hallucinated constants that were very specific for those test cases. In AHC, you actually don't see the test cases, okay? You only know how the data was generated, but you actually don't see the data. So we really have to build good hill climbing sets that span a wide variety of possible inputs. And in response, the model actually learns to generate some more robust strategies because it has to. It cannot overfit the constants to a particular input, right? So you end up with these really interesting sub-problems that are discovered. You can see them highlighted in green, blue, and red. Specifically, I'd like to call your attention to the part in blue, which was completely invented by FunSearch. It basically, you see these double-nested for loop at the top of it. It basically looks at a 30 by 30 subgrid around the particular point and tries to fit a tiny Gaussian distribution on it, right? So it basically tries to figure out how likely it is that this point could be a cluster center, right? And then as a result, it kind of pushes the polygon to go closer to that point if it looks like that should be the cluster center, right? And actually, this is pretty cool because nowhere in the actual prompt we gave to the model did we tell it that this data might be a mixture of Gaussians. So it discovered this purely through evolution and relying on the existing heuristics that it was aware of. And we thought that was quite cool. So when you ask the model to evolve and hill climb over many examples rather than just one, it actually tries these more generalizable strategies rather than if you looked at the previous ones, there's just lots of constants everywhere in these solutions that are very specific to those inputs that we have access to. And this evolved function, without any simulated annealing on top or any other kind of local search, was able to achieve a rank which we bootstrap estimated to be 95% confidence interval between rank 9 and rank 17, which is within the first percentile for that particular competition. So TLDR, we have developed a state-of-the-art methodology for AI-assisted combinatorial competitive programming, and it's based on this FunSearch algorithm, which was already capable of using LLMs to discover new knowledge in mathematical research with the aid of genetic programming. But now it is capable of also achieving top percentile results in historical competitions. That was the last slide I had. I hope you've enjoyed the presentation. I apologize for the slight messiness of my voice because of my hay fever, but I hope it was enjoyable. And I'm happy to take any questions you might have, if either live right now, or if you prefer, you can send me an email or reach out to me via some of my other social media. I once again want to thank you, Sue, and everyone at TILOS for inviting me to give you this talk. And yeah, thank you so much. Happy to take any questions.
Thank you. Yeah, this is really interesting. So I have feel free to just unmute yourself and then ask a question, but maybe let me start with one. Um, So, I mean, you're saying that this helped to enhance the human's capability. And I can see that we need some human expertise at the beginning to build up that robust environment that you're referring to. I'm curious, though, what's your thought on what other domain knowledge or algorithmic insights, things like that, can contribute to this process, or do we just leave it to the to essentially, in this case, a large language model to help to do the hill climbing? Yeah.
I would say we definitely, I mean, if you want to solve the problem as optimally as possible, because of the MP hardness of it, it's unlikely that the AI is going to be able to solve it better than without your input. This is actually a really good example of a problem, which is also respective of real world software engineering very often, where, just letting the AI run, even when you wrap it in a genetic algorithm, I mean, it's going to get stuck in a local optimum. And one thing that we observe a lot, because we've been playing now with trying to allow it to evolve more bigger parts of the code. It just loves to invent simulated annealing everywhere. Okay. And when it does that, it's going to hit a really good local minimum, but you're not going to be able to move out of it very easily because there's lots of randomness, right, which guides the solutions. And therefore, there might be some, materially better solutions which extract better features out of the data distribution that you're simply ignoring by letting it hill climb like that. So I think you absolutely need the human to keep the system in check, in the very least to keep it in check. But also, if you have any particular insight that might help prune or navigate the search space better, that the system might not observe through its reward function, that's also something that's really important. But yeah, that's what I would say is the important aspect here.
Thanks. I have more questions, but I'll give others a chance to ask. Any other questions? Feel free to unmute.
Yeah, I have a question. You were showing like the hacker rank or the competition scores that FunSearch received. Was that FunSearch on its own, or was it through like a human using FunSearch?
This was a human using FunSearch. Specifically, the human, in the very least, wrote the backbones that I showed off before. And often so the self-driving car problem I showed was a little bit easier, the distribution, in the sense that we could just write the first backbone, let FunSearch do its thing, and it kind of give it some hours, and it was able to outperform the top competitors. In most other cases, you had to build specialist backbones for every specific sub-problem that was given, and you often had to adapt them or strap on local search or something, depending on what the AI was given. But the AI itself would be stuck in like a local optimum, and you had to rescue it, as I was describing before. So all the results I was showing was, together with the use of AI, where we were able to land. Certainly, as I mentioned before, none of us by themselves would have been able to reach these scores, at least not in the amount of time we had.
So how do you verify the generated code is actually valid?
So that's the purpose of the evaluator, right? So you prepare, as I said, the environment where you take. I'll actually just scroll back so you can see it for the self-driving cars. So this evaluate function here on the right basically calls the evolve function, which is pick, right? That's the thing that FunSearch is allowed to modify, and then that calculates the score, right? So that gives you the number. And then also that will throw a runtime error if anything that FunSearch did is illegal or, hacks state or, causes exceptions. So basically you have that as your protection against illegal solutions. But I will stress that as most, RL hill climbing things, the model loves to reward hacks. So if you leave any state too exposed, and Python is notoriously bad for this because it's bad at protecting state, you will kind of amplify your scores hugely with a useless solution. So one thing we discovered FunSearch was trying to do actually was rewrite what the file load function is doing to try to invent its own test case. But, obviously we were able to catch that and put appropriate guardrails around it. But basically, the model loves to reward hacks. So you have to be really careful about this. But basically, it's the job of the evaluator to make sure that you're actually climbing the thing that you want to climb, and that solutions that cause runtime errors get discarded. Yeah.
And do you think that the use of LLM is really crucial here, or one could potentially, because you just need, in some sense, a conditional generator over there. So for example, you could use, say, diffusion model that given the current one, condition on that, and then produce the next version of the code. So how much do you think we're really gaining from the whatever, or the knowledge encoded in large language models?
Right. So I would say, from my point of view, the main benefit you get from a pre-trained model on code is that it was exposed to a lot of things humans have done for all sorts of optimization problems before, right? So it's like a really good at taking all of those insights and trying to kind of produce an amalgamated suggestion, which oftentimes will not be something that you would easily think about if you think about the problem for, I don't know, a couple of hours. So it can be really quick to kind of get you off the ground and maybe give you some cool advice. It doesn't have to be a language model. Like, the idea of the genetic algorithm is really the crucial one here. So you could slot in any other mutation function you want. It's just that, code LLMs happen to be kind of an emergent application that was just a really simple one to slot in here. And, conceptually, FunSearch is a really simple algorithm. So, but yeah, totally. You can take this idea in any environment where you might have, you could even involve, the objects you're producing directly, although that might not be as easy to kind of mathematically reason about. But yeah, the idea is very general, and it doesn't have to be an LLM. Yeah.
Great. Other questions? All right. So if there's no other questions, let's thank the speaker again, and then feel free to reach out to him if you have other questions, follow-up discussions. Thanks again, Petar.
Thanks so much for having me.
All right. So